In this lecture, we'll review the types of problems that will be encountered. Then we'll review the problem-solving procedure and talk about one more application to a single unit operation before we start talking about applications involving multiple unit operations. The types of problems we're going to encounter involve single unit operations, multiple unit operations, and then multiple unit operations in which we have recycle and bypass streams. The purpose of these streams we'll see when we start talking about those problems. To review the general balance equation, this class will consider conservation of total mass and of individual chemical species. And the balance equation is of the form that accumulation, A, is equal to input I minus output O plus generation G minus consumption C. Now for total mass, we cannot generate or consume total mass, so accumulation is equal to input minus output. For individual chemical species, though, we can have generation and consumption of individual species due to a reaction. If no reaction occurs, then G and C are both equal to 0. The problems we're going to be talking about today will be ones in which accumulation does not occur. They're steady state problems in which there's no chemical reactions as well, so G and C are 0. So that overall, this balance equation reduces to the statement that 0 is equal to I minus O, or N is equal to out. The problem-solving procedure involves these 9 steps, and sometimes it's iterative. You have to go back and repeat the steps you performed. We're going to find that out. The first step is just to read the problem statement carefully. Then we had lots of practice drawing a process flowchart and labeling streams, and converting all the information we're given to a common set of units. The units in the flowchart will either be mass or moles, or it could be a mass flow rate or a molar flow rate. If we find that there are no flow rates or amounts given in the problem statement, we can feel free to choose a basis for the calculation. So for example, we could assume that we have 100 grams per second of the flow of one of the streams, or that we have 1 kilogram of one of the amounts for the streams. Everything that we don't know, we're going to assign a variable name to. These are all the unknown flows and compositions. Then we're going to perform a degree of freedom analysis. As we talked about last time, this involves counting the number of unknowns and then the number of components and seeing if they're equal to each other. Then we're going to draw a control volume and write our mass balances. We're going to write both an overall balance and individual species balances. And then we're going to attempt to solve for all the unknowns, ideally one variable at a time. Sometimes we can't solve for just one at a time. We have to solve 2 equations simultaneously. And finally, if there's additional quantities that are requested, then we'll have to perform calculations to get those additional quantities. The first example that we're going to look at involves a distillation column. The illustration of a distillation column in a process flow diagram is shown to the left here. On a process flow diagram, you typically will see the column itself drawn with this oval shape. And then you'll see a feed to the column. The one arrow here is labeled as feed into the column. You'll see a product coming out the top of the column. This is a gas that then typically passes through a condenser where it's condensed to a liquid. The liquid is collected in what's called a reflux drum. A portion of the liquid from this reflux drum is fed back into the column. This portion that's fed back is called the reflux. Another portion of this is removed and taken off as a product, the distillate or top product. At the very bottom of the column, a liquid accumulates. This liquid then is removed and sent to a heat exchanger, what's called a reboiler, where a portion of it is converted into vapor. This vapor then is fed back into the column at the bottom, where it rises up to the column. And a portion of the liquid in the reboiler is taken out as a product, as our bottoms product. In a real column, you may have more than one feeds distributed along the length of the column, and you can have more than 2 products. In addition to the top product, the distillate, and the bottom product, you may have multiple side streams pulled off. The picture here illustrates an actual column in a plant, and the other picture here to the farthest right shows what goes on inside the column. The reflux that's produced by condensing, what the gas that comes off the top of the column falls down, and it's illustrated by this blue arrow here, the liquid falling down to the column. The vapor produced by the reboiler rises up to the column. These two streams pass each other, and as they pass each other, material is transferred between them, between the liquid and the gas. And this transfer results in a separation, that what gets fed to the column, that's in this feed stream, can be separated out to produce a higher purity distillate in one of the components in the feed, and a higher purity bottoms product. It's higher purity in one of the other components of the feed. This is one of the most common unit operations in a plant, and is the most common separation process that's used industrially. The column that we're going to be performing mass balances on is shown here. This column has two feeds, a feed near the top and a feed near the bottom, and three products are drawn off: a distillate or top product, an intermediate side stream, and then a bottom product as well. For this problem, all the flows are given as kilograms per hour, and the compositions are mass fractions. If you look at the two feeds to this column, and if you look at both of them, you'll see that we have three components. We have A, B, and C. All three of these components enter the column. If you look over here on the products that are produced, you see the top has been enriched in A. That the stream coming out here is essentially pure A. And you look down here at the bottom, it's been enriched in B and C. And the intermediate stream here, the side stream, has an intermediate composition. So our goal is going to be to try to determine all the unknown quantities over here, all the unknown flows that are designated by an M dot with a subscript, and then all the unknown mass fractions, which are denoted by X, Y, and Z with a subscript. Before proceeding, let's look at this diagram as labeled, as it's been presented to us. Let's make sure that the sum of the mass fractions equal 1. If they don't, or if we haven't made use of that piece of information, we might be able to reduce the number of unknowns in this process flow diagram and simplify our work. First, let's look at the stream over here. If you remember, it was originally labeled as X2 and Y2. However, if we force those to be equal to 1, that 1 is equal to the sum of X2 and Y2, then Y2 can be written as just 1 minus X2, and that's been substituted here. If we look at this stream here, the intermediate side stream, require that 1 is going to be equal to 0.7 plus Y4, and originally, as drawn, as presented to us, there's a variable given for the mass fraction of component C, Z4. If we force the sum of those mass fractions to be 1, then we can write an expression for Z4 as 0.3 minus Y4, and that's been substituted here. By simply requiring the mass fractions equal 1, we've eliminated 2 of the variables that were in the original process flow diagram, and this will greatly simplify our work, and is necessary to solve this problem. Let's check the number of independent material balances that we have for this particular problem for a control volume that goes around the entire column. Well, the number of balances, as we've talked about, is equal to the number of components. We have 3 components, A, B, and C. So the number of independent mass balances is 3. We hope that the number of unknowns is equal to 3 so that we can solve for the unknowns. We know the number of balances is 3. Let's count the number of unknowns. We'll start with this stream here on the left-hand side near the top. In this stream, there's 1 unknown, M1 dot. As we move around, another unknown is M3 dot. As we move down to the side stream, we have 1 more unknown, Y4. As we come down, we have 1 more unknown, M.5. And then over here, for the bottom feed, there's an additional unknown, X2. So if we count these all up, we have 5 unknowns and only 3 balances. So we're stuck at this time. There's no way we can solve for all those unknowns. What this means is that we need 2 additional specifications, that we have 2 degrees of freedom for this problem, that this additional information is needed before we can solve for the remaining unknowns. For this problem, we're going to assume that M.1 is 2,000 kilograms per hour, and We'll substitute that number over here into our process flow diagram. And we're also going to assume that x sub 2 is equal to 0.5. And we substituted that over here. And we know that x sub a, the mass fraction of component A, was a half, and the mass fraction of component B was just 1 minus that. So both are a half. With these assumptions, with these two pieces of additional information, the number of balances will now be equal to the number of unknowns. To solve for the unknowns, we're going to apply our conservation of mass equation, which is of the form n is equal to out, since the process is at steady state and there are no chemical reactions. Let's start with the overall balance, and then we'll consider an A balance, a B balance, and a C balance. As we write each of them, we're going to ask, can we solve for any of the unknowns, or can we combine any of them to solve for the unknowns? So let's start with the overall balance. To write the overall balance, we're going to work our way around the control volume, starting in the upper left-hand corner here, and write down all the stream amounts that are coming in, and set those equal to the stream amounts coming out. So for this stream right here, we have 2,000 kilograms per hour coming in. We'll put that on the left-hand side of the equals here in our overall balance. As we work away our control volume, we encounter a stream coming out. And the flow rate of that stream is m dot 3. We'll put that on the right-hand side of the equals. As we work our way down, we have another stream coming out. Its amount is given explicitly as 1,200 kilograms per hour. We'll put that over here on the right-hand side, along with m dot 5, the next stream that's coming out. It's over here on the right-hand side. And as we come back around, the very last stream that crosses our control volume is this feed at the bottom here, which has a flow rate of 5,300. We'll put that in on the left-hand side to sum with the other feed coming in. This is one equation that has two unknowns in it, m dot 3 and m dot 5. Since we can't solve for either of those right now, let's move on and look at a balance for component A. And we're going to repeat what we just did, except this time we're going to multiply the flow rate of each stream by the fraction of that stream, which is component A. Let's start over here in the upper left like we did before. If we looked at below the arrow, we see that this stream has no A in it. So there'll be no input of A into the control volume from this stream. So let's move on to the next stream, which is 1 coming out. The fraction of this, which is A, is 1. It's pure A. So the amount of A that's coming out is going to be 1 times m dot 3. We'll put that on the right-hand side of the equals in our mass balance. We move down to this next stream. 70% of it, or 0.7 fraction of it, is A. So we'll take 0.7 multiplied by 1,200 to get the amount of A that comes out in that stream and put it on the right-hand side as well. This bottom product stream has no A in it, so it doesn't contribute to the balance. As we come back around, consider this last stream that it passes across the control volume. Half of it is A, so I'll take 0.5 multiplied by 5,300 to get the amount of A that comes in. When we look at this equation, we have this one equation and just one unknown. So we can solve this for m dot 3. We have to do the math. So m dot 3 is going to be a half times 5,300 minus 0.7 times 1,200, which turns out to be 1,810 kilograms per hour. Now that we have m dot 3, let's go back and look at our overall balance. If we know m dot 3, then it looks like we could probably solve for m dot 5, and we're going to do that next. So we're going to substitute in for m dot 3 the known value of 1810 into our overall balance right here. This equation is exactly as what was written on the previous slide. We've just added one more equals, and down in the next line here, written the value for m dot 3 that we now know. This equation becomes one we can solve for m dot 5. And if we do that, we find that m dot 5 is 4,290 kilograms per hour. The values we calculated for m dot 3 and m dot 5, m dot 3 of 1,810 and m dot 5 of 4,290, we've put into the process flow diagram over here on the left. If we look at what's left to solve for, all the variables that we haven't calculated in the diagram here, we see there's only one left, y4. So we're just going to continue to write our mass balances, and the very next species that we can write a balance for is species A, component A. And if we start in the upper left-hand corner, as we have in the past with our balances, we'll determine the amount of a B that comes in or out, comes in or goes out in each of the streams that cross the control volume here. So for component B in the stream here, the fraction of it, which is 0.03, so we'll take 0.03 times 2,000, put that on the left-hand side of the equal sign in our balance. If we work our way around, in the stream here, there's no B, so it won't contribute to our balance for B. The stream here, the fraction of the stream that is B is y4, so we'll take y4 times 1,200, put that on the right-hand side of the equal sign as an output. If we move down to the stream here, the fraction of it that is B is 0.6. We'll take 0.6 times the total, which is 4290, and put that on the right-hand side of the equals as another output. If we keep on coming around, the last stream that we have to consider is this bottom feed, and this fraction of this feed, which is B, is 0.5. So we'll take 0.5 times 5300 and put that on the left-hand side of the equals as the second input. This now is the equation that we are going to try to solve for y4, and it looks like that there's only one unknown in it, which is y4, so we can solve it. If you go through the algebra, the details are shown here, you get a value for y4 of 0.113. So all the values that we have calculated are just summarized here. We found that the value of m.3 is 1,810 kilograms per hour, m.5 is 4,290, and y sub 4, which is the fraction of B in our side stream right here, is 0.113. So we completely solved this problem. Now we're going to talk about applying our conservation of mass equation for balances on multiple unit operations. When you have only one, there's only one choice for a control volume. The control volume is drawn around that single unit operation. When you have multiple units, there's many more choices. You could draw a control volume around each of the units, or around any combinations of the units that you wish, or around the entire process. You can also draw control volumes for mixing and splitting points. The goal is going to be to identify a control volume for which we can solve for the unknowns inside that control volume using our conservation of mass equation, and ultimately solve for all of the unknown flows or amounts and compositions for the whole process. The procedure we're going to follow for each control volume is the same as what we've talked about already. It's just that inside the control volume, there may be more than one unit operation. Example 2 will be our first problem involving multiple unit operations. A stream that contains 30% benzene, represented by a letter B, 25% toluene, represented by a letter T, and the balance xylene, represented by a letter X, is fed to our first distillation column. All of these percents are on a molar basis. The bottom product from this column contains 98% xylene and no benzene. 96% of the xylene in the feed is in the bottom product from this first column. The top product, or the overhead product from this first column, is fed to a second column. The top product from the second column contains 97% of the benzene fed to the column, that is fed to the second column, while the top product contains 94 mole percent benzene and the balance toluene. Let's draw the process flow diagram for this process based upon the description here without labeling the streams. So reading carefully the problem statement, we find that there is a first distillation column, which is drawn here and labeled column 1. And we're told that the top or overhead product is fed to a second column. And you can see the column here. The top product comes out and is fed over to a second column. And the last part of the problem description that is relevant is that we do have a second column. And so the underlined sections here allow us to draw the structure for this process without labeling the streams. Next, we're going to label the streams based upon the problem statement. Now that we have the structure for the process flow diagram, let's label the streams to the best of our ability. Each of the underlined sections in the problem statement will be used for that purpose. First, on a molar basis, we know that the feed to the first column is 30% benzene, 25% toluene, and the balance is xylene. If you look over here in our process flow diagram, you'll see that we've labeled the benzene mole fraction is 0.3, the toluene is 0.25, and we know that the xylene has to be 0.45 for the three of these to sum to 1. The next underlined portion of the problem statement indicates that the bottom product contains 98% xylene. We come down here. That means that the mole fraction of xylene is 0.98. We're also told it contains no benzene, so the mole fraction of benzene is 0. The mole fraction of toluene has to be 0.02 then, in order for these all three of these to sum to 1. The next underlined section states that the top product from the second column over here contains 94 mole percent benzene, and the balance is toluene. That means the mole fraction of benzene is 0.94. Since the balance is toluene, the mole fraction of xylene is 0. There's no xylene in the stream. And to ensure that the three mole fractions sum to 1, the mole fraction of toluene has to be 0.06. All of the other compositions are given variable names. The mole fraction of benzene in the top product from the first column, which is fed to the second column, is represented by the variable y1, the mole fraction of toluene by y2, and we can calculate the mole fraction of xylene by subtracting from 1 the values for y1 and y2. Likewise, for the bottom product from column 2, we're going to assign a variable y3 to the benzene mole fraction, y4 to the toluene mole fraction, and we'll calculate the xylene mole fraction by subtracting these two mole fractions from 1. If we look at the problem statement, we see that there are no flows or amounts specified. In such a case, we can arbitrarily choose a value for one of the streams. And what we're going to do is we're going to assume the feed to the first column has a value of 100. And then we're going to assign variable names for each of the other streams. N1 for the bottom from column 1, N2 for the top from column 1, N3 for the top from column 2, and N4 for the bottom. Now that we have the process flow diagram fully labeled, we're going to move on to trying to solve for the unknowns in this process flow diagram. To solve for the unknown flows and compositions in this process flow diagram, there are several choices for a control volume that we can use for application of our conservation of mass equation. The first choice shown here is what's called an overall control volume. It contains all the unit operations in this process. And if we look at this control volume and the streams that pass across it, we find is that the feed to the first column passes across the boundary for this control volume. The bottom product from the first column passes across it, the bottom from the second, as well as the top from the second. However, the top stream from the first column does not cross the control volume for this overall control volume. Consequently, we don't need to know any of the flow, we don't need to know the flow or the composition of the stream when we write mass balances for this control volume. We just need to know the flows and compositions for those streams that do pass across the boundary of this control volume. A second choice for a control volume is a control volume labeled 1 here around just column 1. And for this control volume, there are 3 streams that pass across its boundary. The first is the feed to the column, the second is the top product from this first column, and the third is the bottom product from this first column. We don't need to know anything about the flows or compositions for the streams that come out of the second column in order to solve the conservation of mass equations for the overall conservation of mass equation or the species conservation of mass equations for the first column. The last choice that we have for a control volume is one around the second distillation column. And there are 3 streams that cross the boundaries of the second control volume. The first is the feed, which is also the top product from the first column. Then we have the top product from the second column and the bottom product. For this control volume, we don't need to know anything about the feed to the first column or the bottom product from the first column. We just need to know what comes out the top of the first column in order to solve the conservation of mass equations for this particular control volume. The question now is, which one should we use? And what we're going to do is determine the degrees of freedom. We're going to perform our degree of freedom analysis for each of these control volumes and see if any one of them can be used to solve for the unknowns, for the unknown variables, the unknown flows and compositions within that particular control volume. Let's see if we can determine if the number of unknowns is equal to the number of equations for these 3 different choices of control volumes. The overall control volume, the control volume around column 1, and the control volume around column 2. Let's look at the control volume, the overall control volume here. Inside this giant square drawn around the whole process, we find that if we look at the streams inside there are 5 unknowns. We have N1, N3, and N4. We don't include N2 because N2 is a stream that does not cut across the control volume. We also have Y3 and Y4. Y1 and Y2 are not in this list because they're associated with a stream that's contained entirely within the overall control volume. The number of equations we can write is given by the number of components that are present within this control volume, and there are 3: benzene, toluene, and xylene. So for this overall control volume, if we were to write apply our conservation of mass equation, we wouldn't have enough equations to solve for the unknowns. We'd have only 3 equations, 1 for each of the components, whereas we'd have 5 unknowns. And because of this, we're going to look at the other 2 control volumes and see if we could use one of those to solve for the unknowns. Let's look at control volume 1. In control volume 1, what we see is that the number of unknowns for the 3 streams that cut across this control volume are N1, which is the flow rate of the bottom, N2, the flow rate of the top stream, Y1 and Y2, which are associated with the compositions of benzene and toluene in that top stream. So we have 4 unknowns. Within this control volume, there are 3 components, benzene, toluene, and xylene, so we can write 3 equations. For this control volume, the number of unknowns exceeds the number of equations, so we can't solve for the unknowns. Let's look at the final choice that we have for a control volume, the control volume around column 2. If you look at that control volume and count the unknowns within that control volume, we have N2, N3, and N4, the flow rates of all the streams that enter and leave that control volume. And we also have, as unknowns, Y1, Y2, Y3, and Y4, for a total of 7 unknowns. And as with the other 2 control volumes, there are only 3 equations we can write because there are only 3 components. So looking at this, if we were to try to solve our conservation of mass equations for any of these 3 control volumes, we'd be stuck because we wouldn't have enough equations to solve for all the associated unknowns. If we go back and consider the procedure that we've described for solving problems, one of the very first things that we talked about was reading the problem carefully. So let's go back and reread that problem and see if there might be some additional information that we can use to reduce the unknowns for one of these control volumes. It turns out there is at least one additional piece of information, and that's that 96% of the xylene in the feed is in the bottom product from the first column. Well, how much xylene is in the feed? The amount of xylene in the feed is 0.45 times 100. Composition below times the flow rate or amount above. So the xylene that feeds the first column is 0.45 times 100, which is 45. The xylene in the bottom product is going to be the fraction of that bottom product, which is xylene, that's 0.98, times the flow rate of that product, N1. We're told that 96% of the xylene in the feed, that would be 0.96 then times 45, the amount of xylene in the feed, 0.96 times 45 is 96% in the feed, is going to be equal to the flow rate in the bottom from the first column, which is 0.98 times N1. This is an expression, an equation that we can solve for N1. We can find that N1 is 44.08, or to 3 significant figures, 44.1, and that number now has been put into our process flow diagram here as a value for N1. Let's go back and reread that problem statement again. We find there is one additional piece of information that we're given, and that's the top product from the second column contains 97% of the benzene fed to the column. Now this type of specification is one that you will commonly encounter when distillation columns are designed, or one of the characteristics that you're interested in. And we're going to look at this the very same way, use this the very same way we used the previous piece of information. First off, we're told the top product contains 97% of the benzene fed to that column. Well, the benzene in the feed to column 2 is just going to be the composition of the feed to column 2, which is Y1, times the flow rate, N2. So that's the feed to the column, the amount of benzene in the top from the second column, is just going to be the composition of benzene in that top stream, which is 0.94 times N1, or N3, excuse me, N3. We're told that 97% of the benzene fed to the column, that would be 0.97 times the flow rate of benzene in the feed, Y1 times N2. That's going to be equal to the benzene in the top product. And the benzene in the top product we just calculated to be 0.94 times N3. So although we're not able to solve explicitly for a value for N3, we find that N3 can be calculated if we know Y1 and N2, and we're going to substitute this expression into our process flow diagram over here. As you can see right below the number 2 here, we have introduced that N3 is equal to 1.03 times Y1 times N2.